Hi there and welcome to this video for Senior Physics on Electromagnetism and Electricity. In this video we're going to explore the last unit in the electromagnetism unit on transformers. Now transformers follows a process of mutual inductance where basically we're going to get two coils where one coil is going to generate a magnetic field and as a result will produce a current or a voltage in a secondary coil. These coils are not going to be linked via wires, they're only linked by a soft iron core. Now you can see an example of mutual inductance in the diagram on the right hand side here. We've got two coils. One coil is attached to a DC supply with a switch S and one coil is attached to a galvanometer. The galvanometer basically will indicate whether there is being current flowing through a coil, and as a result the needle will shift due to the electromagnetism which is generated. So how does this work? Well, basically what will happen is we will switch on the circuit on coil 1, the one on the left hand side. Now before being switched on there is no magnetic field which is generated in the first coil. That's because there's no electricity flowing. But as soon as I switch the circuit on, what happens is current immediately flows and we go from a zero magnetic field to a maximum magnetic field. As a result, I get a change in flux. Now, a change in flux, as we know over time, will generate an EMF, or an electromotive force, which is going to act on the electrons in a coil. Now, what happens is, as the magnetic field is generated, the soft iron core basically enhances that production of the magnetic field and passes it through and interacts with the coil, the secondary coil, on the right-hand side. This change in magnetic field on the secondary coil causes an EMF to be produced, and as a result a voltage is produced on the electrons and a current flows. As a result, the galvanometer meter or needle will basically move. So as a result, I have induced a current into my secondary coil. However, if I leave the first coil on, there is no change in magnetic field over time, and as a result, the secondary coil will drop back to zero. In order to get a further current generated in the secondary coil, I'm going to have to switch off the first coil or the circuit of the first coil. This will mean that I go from maximum magnetic field production to zero. So again, another change in flux. Now you will notice also that the direction of the current in the secondary coil is going in the opposite direction to that in the first. And this basically applies Lenz's law. Lenz's law states that the current will oppose, or the generation of the secondary magnetic field will oppose that of the change in magnetic field generated by the first coil. Okay, so I hope that makes sense. We get this idea that EMF is going to be produced by a change in magnetic field over time. Now this process is the basic process which occurs in ignition coils inside a car or in a transformer. So let's look at what a transformer actually is. Basically it's a device that uses this idea of mutual inductance to increase or induce voltage in a secondary coil. Now this is really useful when we look at moving electricity from one place to the next. We know that if we have to move electricity at high current, this is going to generate a lot of resistance, which means we're going to lose energy. And we'll talk about that later on. So why is AC supply used? Well, an AC supply generally is used with transformers because it switches on and off or changes the polarity from positive to negative 50 times a second. This change in direction causes a change in flux over time, and as a result an EMF is going to be produced. So we're getting this change in current flow, as a result from the generation of the electricity will produce this change in flux. We also need the iron core because what that does is it enhances the magnetic field and basically helps us to produce a larger induced voltage. Now, a transformer can be shown in a circuit using the following circuit diagram as you can see below. Now you can see we've got large coil on the left hand circuit and a small coil on the right hand circuit. The three lines in between represent the soft iron core which basically passes between them. The two dots on either side, the left and the right hand side of the two circuits, basically will show either an input of a power supply and an output which is generated. Okay, so let's have a look in more detail how the transformer works. So here we've got a transformer which is set up. Now you can see on the left hand side it is linked to an AC supply. Remember, AC is alternating current, which means that the poles will switch in the west when electricity is generated 50 times a second. We're going to call this the primary coil. The primary coil basically is the first coil which is going to be subjected to a change in magnetic flux. Now the green area basically represents the soft iron core. So remember, in the coil on the primary coil, what we're going to be doing is increasing the magnetic field, and that's going to be enhanced with the soft iron core, and it's going to interact with the coil on the right hand side. We're going to call that the secondary coil. Okay, and you'll see that as the AC supply flicks on and off, we get a change in magnetic field from going from large flux to low flux and then back in the opposite direction again. So we're changing the direction at which the magnetic fields are generated. That will interact with the secondary coil, and as a result a voltage or output will be generated, and that's represented by the V in the blue circle. Now you will also notice that basically we've got different numbers of coils. Now you can see the primary coil on the left hand side has got more white lines than the secondary coil on the right hand side. This means that on the right hand side less electrons are going to be subjected to the change in magnetic field. If there are less electrons subjected to the magnetic field, there's going to be less EMF produced, and as a result the voltage is going to be smaller. Likewise, I could have more coils on the right hand side and less on the left hand side. That means that the right hand side will have more electrons subjected to the change in flux, and as a result a greater EMF or voltage will be produced. So by controlling the way in which we have the number of coils on the left and the right hand side, we can either decrease the voltage or increase the voltage depending on what the appliance requires. And sometimes you'll find that certain appliances need less of a voltage than is generated from our mains. Sometimes it needs more of a voltage as generated from the mains. And this is why often you'll find that when you pick up an appliance and you pick up the power supply, sometimes it comes in a box, and that box is really heavy. That heaviness is basically down to the transformer, where you've got this iron core which we know is heavy, and then it's going to have a number of coils linked to it. So to recap, primary coil is where you've got your supply coming in. Secondary coil is basically where you've got your voltage coming out, and these are linked together with your iron core. Okay, so we can now formulate an algorithm. An algorithm basically which is set up to say, well, if I've got this much coming in and I've got this many turns on my coil, what is the voltage that's going to be produced in my secondary coil? The algorithm we've got is Vs, which stands for the voltage of the secondary coil, divided by the voltage of the primary coil, will equal the number of turns of the secondary coil divided by the number of turns on the primary coil. Basically, they're ratios. So if I increase the number of turns more than the primary coil, I'm going to get more voltage which is generated. So you can see the two ratios work together. Now, as a result from this, we can produce two sorts of transformers. The first one we've got is a step-up transformer. In this case, the number of coils on the secondary coil is greater than the number of coils on the primary coil. As a result, this produces a larger amount of voltage going into the appliance than what is coming in from the source. Now, the opposite of this is a step-down transformer. Now, the step-down transformer has the opposite, where we've got less coils on the secondary coil compared to the primary, and as a result it will produce less of a voltage than the primary is coming in at. So if you've got a large voltage which is generated by your power supply, but your appliance only works on a lower voltage, you can use a transformer to set that down. Okay, so how does this all link together? Well, what you've got to really understand is if we look at the main national grid which is generated, our power station, as you can see in the diagram here, is going to generate a certain amount of energy. There's going to be a lot of energy which is going to be generated. In this case, we've got 11,000 volts which are going to be generated. Now what we've got to do is to move that electricity across the nation, across the state, from the power station to the various cities. Now this is a long distance. Now we know that if we pass electricity through a large wire, what's going to happen is it's going to generate a huge amount of energy loss. Now we want to decrease the energy loss. Now we can do that by decreasing the current. Okay, if we decrease the current so it's really small, the result is we can get the same power output. And what we want to have is the same power generated in the power station as we get at the house with the least amount of energy loss. So what happens is at the distribution transformer, we step up the voltage. And you can see that the voltage is stepped up from 11,000 volts to between 400 and 500,000 volts. So this allows it to pass through the national grid until we get to the city where we want to go. In this case, we then pass to a district substation. In this substation, it will step down. So we'll have less coils on our VS than compared to on our NS as compared to our MP. So we'll step down the voltage. In this case, you can see it'll be stepped down to 66,000 volts. Now, obviously, as we go from one place to the next, and before we get to our homes, it will be stepped down again and again and again until we get to 240 for our houses. And you'll see these transformers around the streets or around close to your house where it's stepping down before it gets into the house. Offices and factories obviously work on a higher voltage which is generated, and then they will have their own transformers in those buildings which will allow your output, which is coming out of your mains, to be a lot lower. Okay, well I hope you found that useful. What I would like you to do, or what you might find useful, is go and have a look at the final video that I've got where I've used FET to produce transformers and explain how that works. Okay, well I hope you found it useful. That finishes the electromagnetism unit. Do join me again and we'll start looking at how do we use our appliances in electronics to basically convert from AC to DC so that can be used in certain appliances. Okay, well thank you for watching and I look forward to you joining me again.